Let me check online real quick. My schedules have changed just a little bit. I got your email this morning, Gunnar. I didn't even know that you were. Did you respond back, Gunnar? Are you going remote, or are you just out for a quarantine? I see Jenna. I see Jace. And I don't know who is remote and who is in person. Everything is chaotic. I think we have till 10:15. Okay, I don't think that child's here anymore. I don't see Sheila. What? Good.
First try.
Jenna's online. The hero's here. I don't see Jade. I'm so sorry. Give me just a second to let me. Guy is here. Parker's here. Brian's here. Tyler. Sharon, Ava, Ta, Amanda, Hernan, Hunter. I don't see Brandon. Okay, Jace is online. Isabel's here. Josh is here. Gunner's online. Nathan's here. Nathan, pull your mask up, please. Johan. Kiwi's here. Okay. Yeah, everything's all kinds of crazy. I've got a chat bubble. Hang on here. All right, we're gonna see if we can get through all of this first period. We only got halfway through, but that's because the announcements went so long. Was there anybody that needed a paper copy of this and is not wanting to do a digital version? Okay. Oh, you are here. Okay, hold on here. I got your thing in my cracker, but I don't think it's gonna pop it. Yeah. And I forgot to bring my picks. We're sort of picking up where we left off before the break, which I know you guys took 2 weeks off and enjoyed it and did not study my class. We started with plate tectonics right before the break. And why is this not unfreezing? Why are you not unfreezing? I think my batteries are dead. There we go. We started with plate tectonics. That was actually supposed to have been finished in first semester, but since the second 6 weeks was only 5 weeks long, everything just sort of got bumped back. So we're going to talk about a few things that let me make sure I'm recording. Yes, I am. We're going to talk about a few things that we mentioned before the break because you don't remember some of it, and then we're going to go into depth. How do we know? How do we look inside Earth?
With some sort of like technology.
It is with some sort of technology. That's exactly correct. But look,
I know what it is.
You don't know how to explain it. Well, so let's try the second half of the question. Can we dig into the core?
No.
No, why not?
It's too hot.
Yeah, you come in contact with magma, what happens?
It just melts.
Yeah, you're dead. You're melted. I don't think it's even the right phrase for that. You're vaporized. You don't survive. In this particular section, to my knowledge, and I did fact check myself a bunch over the break, how deep we've actually been able to go. There are limits to how deep we can go. You go too deep, you come in contact with magma, and you die. You can't. So what we use to look inside the Earth, we either use natural or man-made earthquakes. In first period, they kept calling it sonar. It's seismic. Sonar is very close. Very close, but they're called seismic waves. Right. Sonar, well, but sonar doesn't have to go through water, it can go through air, but you're still listening to the echo. You still are. But it's not, it's not seismic. Seismic waves.
How do we see it?
By essentially looking at the echo of an earthquake. They're called seismic waves. It's not technically sonar. So we're going to go back a couple weeks ago. Wegener in 1912, when technology was starting to pick up with electricity, and I mean, we didn't have satellites or anything back in 1912. He was the first guy that theorized continental drift. Now, continental drift was thrown out the window, but it was the stepping stone into what we call plate tectonics. The big thing that Wegener did not know about was the oceanic crust. He knew about continental crust, but it's called continental drift. And he didn't know there was a different type of crust. And before the break, when we did igneous, we know that oceanic is much more dense. It's got more basalt. It's got heavier elements in it. It goes down underneath those continental plates and lifts them up. He just didn't know. It's not that he was dumb. He just didn't know. And his theory was thrown out by his colleagues because there wasn't enough proof. We didn't have the technology. And he was on the right path, but continental drift wasn't right. I said it was sort of that stepping stone into plate tectonics. In fact, this poor dude, we didn't get to this in first period because I tried to do 45 minutes and like 20 minutes worth of time. But this poor dude, trying to prove continental drift, he went to Greenland in 1930 and he died. He succumbed to the elements. He was trying to prove his theory. He was trying to unearth different things, and he died. Exposure. But he was in Greenland.
Greenland's the opposite of Iceland, which is completely snow.
Now, Iceland's volcanic. Greenland is not. It's ice.
They named it confusing for Vikings named it. So maybe
Yep.
like opposite, so people would go there and die.
Correct. He's 100% correct. In fact, I have a next week. I have a documentary that we'll watch on Iceland specifically. Iceland's really weird. It's literally being torn in half.
I mean, it's just giant shit. It's like, that's all it is.
For Iceland,
Or Greenland.
Greenland's yes, it's a glacier. Now, along the edges of the fjords, that's different, but most of it's just a giant glacier. Iceland, on the other hand, is not that way. Seems like they finally fixed my heater. I know, like, maybe I should turn it down. Is it too hot? I mean, I have it set on 78, it says it's 68 in here, but I'm almost afraid to touch it. Let's see what happens. I don't want to sweat, that's gross. All right, so you fast forward 60, 70 years from his original hypothesis of continental drift, and we get satellites in space. And peering through space and then into the planet, they actually map. It's called topography. They can map the bottom of the ocean from space. He just didn't have that. He didn't have understanding of the oceanic floor. He didn't have understanding that the poles reverse every 500,000 years. He didn't have a seismograph. He didn't understand the things that we understand now. But he was still sort of that first person that led us in the right direction. And then he ran off to Greenland and died. Very cold there. We mentioned this part before the break, our plates. There are lots of plates. There's 12 major plates and there's a bunch of little minor plates. They're literally riding on top of the asthenosphere. The mantle is not technically liquid. It's plastic. Not like this kind of plastic. But it's like a very, very, very slow moving solid, just like that window. Glass moves. it sinks over time. It just takes hundreds of years for you to notice that it's moved.
That glass.
It will be thicker at the bottom and will be thinner at the top.
Oh.
Now, around here, most of the windows aren't old enough. But if you go up to the northeast with the really old churches that have been around for hundreds of years, they bulge at the bottom. It's just, it's hard to explain. I come from really close to Philadelphia, and I've seen it as a child. It's like, it does almost like an hourglass thing down at the bottom. Very, 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 very long period of time is necessary. So technically, glass isn't 100% solid.
So, pretty much, glass is melted.
It's not melting. O'Brien. Steve had wants to see you. Should you take his stuff? Okay, I don't know. I don't know. You know better than me. I don't know, Brian. I mean, can you like just stick your hand through glass? No. Okay, but it does very, very, very slowly move, just like the interior of the earth. I'm sorry. Did anybody still need that? You need to go back. Yeah. Okay. I apologize. No, it's okay. I thought there was one more layer. Or one more bullet.
But it's just like, I have a part of my.
Right. Yeah, I don't know if this puppy is going to open this or not. But I have it set up to try to get it to go. I just forgot to bring a cracker. No, it's a cracker. Cracker.
It's a Geo, right.
And I bought one of these over the break. Now, but if it's really solid, it won't pop it.
Geos, I remember when we were opening Geos.
Now, I bought my kid a bunch of them over the break. She may have some that are a little bit more. This one's pretty dense. I would be surprised if that opens that. And I forgot to bring a wrench to be able to torque it. We'll see. We'll see. All right, so to my knowledge, and I did fact check myself, for a very long time, the deepest we ever went was a Russian borehole that was finished in 1989. It took them like 20 years to like dig that far down. Huh? Yeah, where it sounds like people were screaming in hell down at the bottom of it. Yes. I can't remember the name of it, but that has been superseded in Qatar, which is how you pronounce that. The deepest well or borehole that we've done is this particular oil well or borehole. Same thing. We still can't go into the mantle. We will die. We'll burn. We'll vaporize. Burn isn't even the right phrase. You crushed to death.
Make a hole. I'll jump in.
But how we do look inside the earth, we use what are called seismic waves. And this is how you spell seismic, whether they be natural, which are earthquakes, or we use man-made versions, which is actually how we find dinosaur fossils now. We don't just go dig. You percuss the ground and then you listen to the echoes, and it literally shows you where the bones are. We do the exact same thing to the center of the earth. Depending on how they bend or how fast they move, or if they go through something or not, lets us know the interior of the earth. Don't worry, I'm not going to make you do any kind of mathematical stuff on that part. We will do a little bit of logarithms when we get into earthquakes. It's not hard. It's smashing buttons on a calculator. It's not anything crazy. But we do know that the diameter of the earth is approximately 7,500 miles, give or take. It's not exact. But knowing that, and then being able to look at how the S and the P waves, which I could go a lot more in depth, but in general, the S and the P waves, how they bend and how fast they go and where there's shadows, lets us know how thick the crust is, the mantle is, the outer core and the inner core. I have people asking me, how do they know that this is so thick and that is so far and blah, 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 blah. And I was like, I don't know. It sounds like I got things going on. I'm gonna check. Let's see, I'm hearing dingy noises. Well, I don't know what I was hearing. I'm not. It's probably an email. Yep. Just don't do whatever it was that had them shut down before the break. I think it was graffiti. I don't know. Either that or somebody pooped on the wall. I don't know. But they were locked down. They were locked down before the break. That was annoying. We'll go forward. I know with first period, we're going to have to come back and take a look at this. We only got halfway through because those announcements took so long first. So I'm used to doing this from a physics perspective. If you have a wave that hits something and bounces back, it's called a reflection. Okay, so you're standing in front of the mirror and the light waves hit that silver substance that's on the mirror that makes it shiny, bounces back into your eyeballs. That's why a reflection is called a reflection. It is a reflection. So sometimes an S or a P wave strikes something inside the earth and bounces back. Sometimes, as it goes through different densities, it bends, which is called Snell's law. Which, I mean, I could detail Snell's law. It's not hard. A little bit of trig. It's not bad. But as you go from something that is less dense into something that is more dense, or vice versa, if it's more dense, it gets bent in. If it's less dense, it gets bent out. Y'all, that's why when you stick a straw in a glass of water, it's in a different place. It's not really in a different place. Or for those of you that are fishermen, you know that fish is not where it looks like it's supposed to be. I mean, if you're good at it, you know where you're actually supposed to throw because the light bends in a specific direction. That is called refraction. If some of the energy seems to disappear, it's absorbed, especially over long distances. It goes from point A to point B. That's called attenuation. Oops. Let me go back. I apologize. What's not? I miss taking physics so much. The other word that can be used when it comes to light is called diffraction, which means it spreads out as it travels through an opening. So if you're trying to sleep and your bedroom door is cracked and there's light outside of the room, how it looks like it spreads out as it comes through the door, that's called diffraction. But that's not. Seismic waves don't do diffraction. Like I said, we're not going to mathematically map these. I spent a good solid week doing 2 weeks worth. I so want to do the entire 6 weeks over the break. Yeah, I didn't. But I made it through 2 weeks. Yes, right. If they are shallow, you get very fine detail. The deeper into Earth you go, the less detail you're going to see. Very similar to what you think of as sonar. It's a very, very, very similar process. In this particular cross section, which I don't know where this one's taken, you can see the different densities as you go deeper into the Earth. I don't know what any of them are specifically constructed of. I didn't go that far into it. But in a very, very, very shallow depth, both S and P waves reflect and refract and give us very fine detail. Now, this is obviously an animated version. When we're talking about deep into the Earth, some waves, and the black lines are S wave. Well, let me make sure I'm not saying it the wrong way. The black lines are S waves and the yellow lines are P waves. S waves, they can't go through a liquid. They can go through a solid, but they can't go through a liquid. A P wave can go through both. And we'll get more in depth with this as we go on, but we have these areas, these shadows where there are no waves. Now, if it's an S shadow, this entire bottom part, there are no S waves. S waves can't go through a liquid. So as soon as they hit that outer core, which is a liquid, they can't go through it. So we have this area where there are no S waves. P waves are different. P waves can go through a liquid. Now, because of when they strike this outer core, they refract, they bend, just like that fish. It's not where it's supposed to be. Oh, so it's not where it looks like it's supposed to be. And these bending waves cause smaller shadow regions. Like I said, this entire bottom part down here, there are no S waves, but there are certain sections where there are P waves and where there are not. All it takes is a little bit of geometry, and we can calculate how thick each layer is. Like I said, we're not going to mathematically do this. But that's, for those of you that were asking me before the break, how do they know how thick this is? This is how they do it. It just took technology to have seismographs to be able to record earthquakes, whether they be like natural earthquakes or man-made. All right. The farther the wave has to travel, the more energy is absorbed by the earth. That's what attenuation is.
So solid could also be more dense in this situation.
Solids are going to be more dense. Now that's not the only thing that affects a wave, okay? But the density is one of the primary things that affects the wave. The more dense it is, the faster the wave goes. P waves are way faster than S waves, just in general. But as they're going, well, S waves don't go through a liquid. But a P wave, as it travels from the outer core, which is a liquid, to the inner core, which is a solid, it shifts its speed. If it's hotter, it's going to move slower. If it's colder, it's going to move faster. The inner core is way hotter than the outer core. And S waves can't go through liquids. S waves can't go through liquids, they can only go through solids. P waves can go through both. And it gets a little bit more complicated than just S and P. There's PKI KPs, there's TCPs, there are SCPs, there's all different kinds of like subcategories. We're not going to go into them. You can see them on some of the images, but we're just not going to go that far into it. I don't have enough time to go into it, considering that this stuff should have been done last semester and we're still trying to cover it. I'm really not that concerned. The 6 weeks is supposed to be climate change, and I can do climate change in 3 days. We will actually start climate change with this section, the plate tectonic controlled climate change, not the greenhouse industry carbon dioxide climate change. There's so many different types of climate change. All right, angle of incidence. Incidence, and I know a lot of you have not had physics. An angle of incidence is the angle that the incoming wave strikes a substance. Incoming is incidence. How straight on or how sharp of an angle is going to control that bend. I said, I could go into Snell's law, but we're not going to go into it. That was something I did with pre-AP physics. I didn't do that at all with my regular physics kids. Your layers, they control this too. And we're going way back. We're talking about original horizontality and superposition. But I'm not going to mathematically ask you to calculate these angles. I don't see how I would have the time to do it. Resultant means it's the result. It's, now let me de-physics that line. The vertical arrangement of layers controls the resultant direction of travel. How they're stacked depends on how it bends. That's what it means. Resultant just means what it turns into. It's the result. Have any of y'all had physics?
Nope.
You have had, okay, so you actually understand a couple of the phrases that I'm saying.
I
Okay,
do a little bit.
it's, oh man, I love physics. Physics is great. It's so easy. It's just, it's geometry and algebra. It's so simple. Well, if you hate math, there's two ways. You can either do completely conceptual physics, or you could do more analytical, which I have an analytical brain. That's how I taught it. I'm not talking about mechanics. I'm talking about physics too. I'm talking about that. It's calculus. Ugh, nasty. But no, it's physics is so easy. It does depend on your teacher though, a lot. All right, P waves and S waves. And we're going to see, like I said, we've got what, according to the bell schedule I saw on the computer, we've got like 12-ish minutes. I don't know how messed up my clock is. P waves are called primary or pressure waves. That's what P stands for. They are the first to arrive with an earthquake. They are, I need to bring my slinky out. Dang it. It's over there. It's a pressure wave. It's a longitudinal wave, which is also physics term. Where did I put my slinky? S waves are different. They are, here we go. S waves are shear waves or secondary waves, and they are transverse. I don't know how many of you know this phrase. You know, so transverse to this, okay, transverse to this. Pressure waves, Slinky's are physics teacher's best friend. Pressure waves do that. Okay, so, and they're different. Now, when they both reach the surface, then they combine in a surface wave. That's what does all the damage because you've got these pulses and you've got these back and forth. They go this way and this way. And when we get into earthquakes, we'll talk. One of them is called a rally wave, and the other one's called a love wave. And those are the really damaging things that tear stuff apart.
What does the love wave look like?
Let's see if I remember right. The really damaging one is this one, and that is a. I want to say this one's the love wave, and this one's the rally wave.
Yeah.
I might be backwards. I mean, they're still both going back and forth, but one is going this direction. It's this one that's the really damaging one. Yeah, it just tears them off the foundation. Yes. This is I actually rather enjoyed researching how to do this over the break. I never, what, huh?
By the way, how was it?
Not long enough. I did get a year older though. No, it sucks. Wait till y'all hit that point where getting older is just another reminder that you're just getting that much closer to death.
Hey, my mom turned 60 in January.
Oh,
I turned 20 in November.
Lordy.
No, I turned 20. Yeah.
All right, so a seismograph. A seismograph is a machine that essentially listens to the echoes of earthquakes.
What?
A seismograph. It's these machines.
No, I
We
know it was.
set them up all over the planet, and they listen to these echoes, for lack of a better word for it. And then they, on this drum, this little needle goes back and forth. And that's how we understand how strong an earthquake is, which is measured on what's called the Richter scale. knowing where the focus is, which you probably have heard of it, is called the epicenter. Not exactly the same thing, but where it starts and where it goes to, and how much of it has been attenuated or how much of it has been refracted, lets us know. Now you have to have at least 3 points. It's called triangulation. At least 3 different seismographs to be able to figure out where an earthquake starts from. If you don't have at least 3, you can't triangulate. It's the same thing that they do to figure out where you are. And you have to have at least 3 different what are they called? Towers, cell phone, whatever those things are called. You have to have at least 3 of those to figure out where you are, which y'all don't think that they know exactly where you are and what you're doing.
Oh, yeah, they can probably watch it from the camera.
They do. They do through your television camera, by the way.
The television's got cameras?
Yeah, they're newer. What?
What?
Yeah, they do.
Yes.
Yes. The government knows more about y'all than, I'm not trying to be all conspiracy theory, but they know a lot. They know a whole lot.
It's not even doing basic.
Okay, I don't know if we're gonna be able to finish 100%. I've got a few more slides. This one is just images. So this is what a seismograph looks like. It's got a paper on a drum, okay, and the paper gets fed a certain way. And then the needle, if you have seismic activity, it makes it shake back and forth. Probably on the next one. Oh, did I have it on the last one or is it on the next one? The S wave shadow is larger because it can't travel through a liquid. If it was not on that one. Here we go. I stapled my stuff backwards, so. Okay, an isopac contour line. We will eventually get into how to read a topographic map.
I love it.
This is, oh, they're easy. And
That's so cool.
eventually I'm going to start building stuff in where you guys would make your own, like 3D one, but I don't have any of the foam stuff to do it. So that's probably gonna be a next year thing. But an isopac contour line, it's same elevations like planet wide, not just in like a hill or a depression or a mountain. This is sort of a tie-over from before the break. Oceanic crust is thinner, somewhere between 8 to 10 kilometers thick, give or take. It is more dense because of the more dense materials, the basalt. The continental crust, anywhere between around 30 to 80 kilometers thick. So like the 80 is Mount Everest. The 35 is like at the shore kind of thing. So it's got a wide range. It is much less dense because it's primarily made of granite, which is a lighter elemental composition. Oxygen and silicon. Where they come in contact, which we talked about boundaries before the break. We're going to come back and do it again because you probably forgot. But when they slam into each other, your more dense, which is oceanic, subducts or goes underneath the less dense, which is the continental. Now, when they subduct, eventually they get stuck with the continental that's going on top. And if it snaps into place, that's where we get tsunamis from. Which we'll talk about those later when we do earthquakes as well. Tsunamis are not anything to mess around with. Tsunami. Yeah, and the tsunami, I guess, country of the world is Japan. Tsunami is actually a Japanese word. But the largest tsunami was the Chilean one that happened in 1964. And it went all the way across the ocean. It almost took out Hawaii. It was like 80 feet tall. It was huge. It's not that big. You'd be like, okay, 80-foot tall water wall.
I'm not a wall.
I will say if you are ever at the beach and all of a sudden the ocean seems to recede, run, go up.
Isn't that also just, wind stuff?
No, the tides, no, I'm talking about like the whole ocean gets sucked into the ocean.
Yeah,
Like,
it's
just
like,
getting
it's
more
not
into
small,
it.
it's.
And people are like, oh, look at all the starfish and the clams, and then, oh crap, here comes.
Yeah, but if you're at the beach without a phone, you can see
Yeah, but don't you see it?
If I ever go to the beach, not see that, I'm running to my car and driving as fast as possible.
Okay, we're gonna see how, I'm gonna have to make notes on here where we get to. Where we at on here? We are on, here we go. The Mohoro Visick. Okay, the Moho, this is the boundary. Well, so the crust is on top, and then you have this discontinuity, the Moho, which is short for this. And then underneath that is the asthenosphere. Named after this particular, I want to say he was Russian. It sounds Russian to me. Named after the individual that figured it out. A lot of this is more review from before the break. I just know that you've forgotten. Oh, is there anybody in here that did not take their 6 weeks test? I had sent out an email. Okay, so Jessica and Isabel. Okay, so I have to reopen it. It wouldn't record. Like, I actually had some people that took it on Friday the 18th in my chemistry class, and because it was outside of the scheduled, like, it wiped their test. So I will open that back up probably during next period because I don't have a class next period, and it's just a matter of and then let me know. Just shoot me an email and tell me I took it so I can get it into the grade book. Because I won't know if you don't tell me.
I got 42 in 6 weeks last week, and my Wi-Fi was off, and my
It's-
parents were not home. So
It's I have so many different situations that happens. It's just a matter of taking care of it. Okay, I am going to. We're actually not that far. I'm gonna stop this here. I know we have a minute. I mean, I can put up the next one if you want me to. So we are in seconds.
Yeah, like, I'm on.
I already know Diamond.
I know, and I don't want to rush it. I want to rush it.
What is it?
I don't even remember what I asked for number 10.
Controversy every 5,000 years.
years in which process?
Aurora, super spreading, and magnetism. No,
Is it solar intrusion?
Auroras.
Get to it. Let me double check my attendance real quick. Make sure nobody else came on. I wasn't expecting to have an abridged bell schedule like this at all. Like, I didn't even know that until this morning. So, okay, I don't see. Let me stop the presentation. All right, we will pick up and finish this. So.